When we look at light, we're going to break it in a couple different pieces, and the main parts are the wavelength and frequency. Okay, so one of the main equations that we look at associated with light is the speed of light and the wavelength and frequency associated with that, because it gives us a nice relationship between wavelength, which is our like little triangle kind of looking guy there, and our frequency, which is a funny looking V, and how they're related to one another with the energy that light is putting off. Okay, that particular amount of that particular type of radiation has. So things like X-rays, when they take your X-ray, it just goes, and then it's done, right? So it's like just a split second worth of radiation is enough to get that X-ray. All right, a lot of very high power. Your bones and different things absorb that radiation more than others, so then you get a nice contrast on the film there. Okay, where the visible spectrum of light, very small spectrum of the overall electromagnetic spectrum there. Okay, so if we look at these, they're between energy, frequency, and energy. Okay, they are directly related, right? Because as frequency increases, energy increases. Okay, so that's a direct relationship. And wavelength and energy are inversely related. Okay, so that's an inverse relationship. So, when it comes to radio waves, they're very big, long waves, but not much energy in them. Okay, ultraviolet rays, much shorter wavelengths, a lot more energy there. Okay, so they're inversely related. Something also too is that we want to touch on a little bit is amplitude. Okay, so amplitude is just basically, all right, if you've got the stereo cranked up, or is it playing very soft? Okay, still it's the same wavelength. Okay, but it's just a matter of amplitude. Is the light really bright? Is the sound really loud? Okay, but it's still the same wavelength. All right, which ultimately means it's got the same amount of energy in there. Okay, so it's just kind of its intensity in terms of like how bright the light is, or you might have a really bright red light, or it might be very dim red light. Still the same wavelength of light, though. Still that same wavelength of red light. Okay, does that make sense? All right. So a couple things about units for this one. We've got a couple units that we want to be aware of. One is nanometers, right? So that's our NM, right? So if we have 1 meter, that's equal to 1 times 10 to the minus 9. Or I'm sorry, not minus 9. I'm just going to get that out of the way. Move it. Whoa. That was fun. I didn't know I could do that. Okay, whatever. This is, I'll pull out the eraser. There we go. That's better. Okay. All right. 1 times 10 to the 9 nanometers. There we go. Okay. Yes, it is. That wasn't hard enough. Okay. So we got that. We'll look at some hertz too. So with hertz, so when you listen to B96 in the morning, the Yahoos that are talking on there, that's what we're talking about, the frequency, 96.3 hertz, right? All right. Usually that's expressed in per second. So you might see it as 1 over seconds or seconds to the negative 1. All right. So those are going to be that right there. Okay. Okay. All right, so if we want to utilize that equation up above, right, in terms of our speed of light equation, and that's why we need to know how many meters there are in nanometers. So if we flip to the next page here, all right, we've got some fireworks. When you're looking at fireworks, fireworks are, we'll talk about, kind of like emission spectra today too. So if we look at this stuff, when we excite electrons in atoms, and then they go up to a higher excited state, and then those electrons fall back down. They got to release energy in some way, shape, or form, and usually they release in the form of radiation, right, or light. And then sometimes we can see that light. So for fireworks that have strontium in it, they'll look red to us because they're emitting light that's around 650 nanometers. So if we want to calculate the frequency of that light, all right, we got to do something first, right, because we have wavelength, right, and we have frequency, and they're related together with C here, right? So if we go to do this, we want to solve for frequency, my funky looking bee with wings. We got speed of light divided by wavelength, okay? So the speed of light is 3 times 10 to the 8 meters. But issue is we've got nanometers. So we need to convert nanometers, 650 nanometers into meters. So the way I'm going to do that, so in 1 meter, there are 1 times 10 to 9 nanometers. Okay, so we're going to divide 650 times 10 to the minus 9, which, can you do it without your calculator? Yes? Oh, that's just the speed of light. That's C. That's just a constant. Yeah, sorry. I think we talked about that when you were in the bathroom. So now everybody knows on the internet that Maggie missed the... I'm just joking. All right, so 650. I am recording though. 1 second e to the minus to the 9.
We need to get to start the lesson over
Oh, yeah. All right, so 6.5 times 10 to the minus 7 meters. So you'll notice if you're trying to convert stuff from nanometers into meters, it's always going to be, if you have 650 or like a lot of things in visible spectrum are all in some 100 nanometers, right? So you can always just put a decimal in there, times 10 to the 7, boom, you're good. You're there in the meters already, okay? So, and you'll deal a lot with things in the visible spectrum light. So then we plug that in there, 0.5 times 10, 7 meters. Oh, sorry, light is meters per second. So we'll be left with hertz, because meters are going to cancel, and we left in per second. So 3 to the divided by, so speed of light divided by 6.5, so e negative 7, we get a massive amount of hertz. So 4.62. I got times 10 to the 14 seconds. Okay. There we go. Okay. All right. So as we get into light and what's going on here, we'll get into a couple different things here. So light, right? Like when you're in your, yes. Same thing. Yeah. Like you could have hertz here, or you could have your units in seconds like that. That's all the same thing. They're all the same. You could do it all in any way you want. Okay. So like when you're in your house, okay, and you're in your bedroom or something like that, and you don't have any lights on in your room, but the light is on in the hallway, light still gets into your room, right? Okay. Acting like a wave, right? It's like bouncing off the walls and reflecting and all that sort of stuff, right? Okay, so you got that wave-like property of light, okay? There's also this particle-like property of light too, right? That they started, that they came up with, Einstein and Planck and all these guys. So we're just really waving our hands at the fact that there's going to be two, that light is wave and particle light, okay? It's got properties of both. It does both things, okay? So the reason why that is so I'm going to go down here to the photoelectric effect. Talk a little bit about the photoelectric effect and what that is, okay? So this is what Einstein actually, basically, he explained the photoelectric effect and won a Nobel Prize for it in 1921. Okay, so, and I'll show you a little picture of what we got this little online simulation that kind of is pretty cool. So Einstein wins the Nobel Prize in 1921 for his explanation. You don't need to know this, but I'm just throwing that in there, of this. And basically the photoelectric effect is the observation that many metals emit electrons when light shines on them. Okay, so the photoelectric effect is basically we're going to take a piece of metal in a vacuum, we're going to shine light on it, and it's going to run a current. So it means it's moving electrons. So that was like, whoa, that was like mind-blowing, okay? Didn't know what was going on with that, but then Einstein, you know, comes up with this whole idea, and we'll get into that a little bit. So I'll show you an example of the photoelectric effect. And let me see if I have it here. Yeah, okay, here's my photoelectric effect. Little picture guy, okay? So right now I've got green light, 100% intensity, and I have my metal, where that little gray part on here. So the metal is right there. I can't draw on that. And that's sodium, okay? What I'm going to do is I'm going to change the wavelength of light I'm putting in there. I'm going to move it more down towards the ultraviolet blue area here. And what do we get? We get electrons to move, okay? Because we get current, right? Current is the movement of electrons through the wire, all right? That's just by shining the light on the metal. So what the heck? How is there, if we're getting, there must be energy associated with that light, okay? Now, I can go to the ultraviolet light, right? Ultraviolet, don't go to the tanning bed, okay? Lots of energy in ultraviolet light, and that's what you're bathing yourself in, up close and personal in the tanning bed, okay? Lots of energy there, okay? And then as I move it way back over here to the red, oh, not much energy there. Not even enough, really. I'll get that guy over there and done. Okay, there's not enough energy in this light to promote electrons to run. Okay, so the idea here is that, all right, what's happening with this? We're shining light on here, but what's the difference between this light and that light? Got to be something different there. Okay, and the way that Einstein kind of explained it is like, all right, well, let's try to take it down to the smallest part. There's got to be some packets of energy that are hitting that metal with enough energy to dislodge or dislocate the electrons and get them to move. Okay, and he called those particles of energy, those packets of energy, photons. Okay, that's where the idea of a photon comes from. So the way the light is not only behaving like a wave, but also there's a packet of light, there's a packet, like a photon, traveling in that wave as well. So when we visualize that, I'm just kind of thinking, we visualize it a little bit like this. This is how Miss Mars and I think about it. If we have light, it's acting, it has a particular wavelength, but it also has a particle or a photon associated with it. So these circles here are photons, right? And our photons are just a packet of energy. Okay? Our photons are just a packet of energy. So what we do when we think about this is, okay, well, the red light, its photons must be kind of small. It doesn't matter if the light's really intense, right? Huge amplitude. Doesn't matter, because the same amount of energy is still going through there, okay, in the photons. But the blue light, it doesn't matter what kind of blue light we show on it. The photons in the blue light, there's more, the packet of energy is larger. So it's able to hit the metal with enough energy to dislodge that electron and push it off of the metal to get current to run. Okay, so that's kind of what's going on. So now this basically, and Einstein took like the next equation that we're looking at now. We kind of did this a little bit out of order, but Planck came up with this idea of how much energy is within a photon and stuff. Okay, so but the idea here is not only is light behaving like a wave, but it's also like packets of energy coming out as well. Okay, and they're continuously coming out. And the way he was thinking about it is that you turn the light on and off as quick as you can possibly do it. Okay, the split second that it's on would be releasing one photon at a time, and it would behave like a wave, but it would pack that amount of energy in with it. Okay, great. Then I feel like I confused everybody. It's great. Okay, it's good. It's good. It's good. Okay, so we got photons. Photons are packets of energy that can displace electrons in the metal. Okay, and these packets are of varying amounts of energy. Okay, thus we have the whole dual nature of light. So light behaves as both behaves as a wave and particle. Okay, so it's behaving as both a particle and a wave. So light travels around corners like waves in a pond with like you throw a pebble, a pebble into a pond. It creates waves, and it will go around those waves will travel around objects in the pond as well. Okay, and meet on the other side. Right, just kind of like similar to the moon. Right, you had the moon the other night on Sunday night. There's a reason why I turned that reddish color. Okay, as the moon came into the Earth's shadow, there's still light that got refracted to hit the moon. And that was the light that made it through from the sun through the Earth's atmosphere that actually made it was the lower energy intense red light. The higher energy light, the blue light, the yellows, the greens and stuff, all got refracted. So, but the red light made it through. Okay? So, because there's different particles, depending on what, you're talking about a huge amount of atmosphere that light has to pass through. There's lots of different particles, and different particles absorb different wavelengths of light. Okay? And then they reflect different wavelengths of light as well, too. So that's why the sun is yellow when it's up high in the sky, but as it sets, the amount of atmosphere that the light needs to travel through increases to your eye. Okay, when it's right up above you, it's traveling through the least amount of atmosphere. Okay, so that amount of atmosphere makes the sun look yellow and the sky blue. As the sun begins to set and the light travels through more and more atmosphere, more and more of the light gets refracted and reflected and stuff, so now the sun starts to turn different colors, and so does the sky at the same time. Pretty cool stuff. Okay. Boom. Sky's blue. That's why. All right. So moving on. We didn't really. That was about it. Okay. So. All right. So here's Planck. So this is what Einstein used Planck's equation here that he came up with to actually talk about those packets of energy. Okay. Because Planck was able to figure out. Okay. That this is per atom, this energy here, and this should be pointed at that E, okay? This is joules per atom, or joule, that we're looking at here, okay? So the energy that comes out here with the E is joules per atom. That's the unit of that guy, all right? That's going to be important for us to know that. So Planck figured out that each one of these is 6.62 6.626 times 10 to the minus 34 joules per second is his constant that he's using here to associate with frequency too. So, but we can also use, from our equation that we had on the first page with wavelength relating frequency to the speed of light, we can also set that up in there, right, and have h times c over the wavelength, right, because frequency is equal to c divided by the wavelength. I'm subbing that in there for frequency. So depending on what we're looking at, like if we get a wavelength of light, we can solve that equation that way. If we have a frequency of light, we can also solve for the quantum of energy there as well. Okay? All right, and kind of going off of this, we can do a couple other things as well. Okay, so an example problem that might correspond to this type of equation here is another firework problem. Okay, but we've got blue light being emitted at 450 nanometers. So as soon as I see nanometers and things like that, we want to convert that right into meters right away. So I'm going to multiply that guy, 1 meter divided by 1 times 10 to the minus, or times 10 to the 9 nanometers. So that's going to give me 4.5 times 10 to the minus 7 meters. Okay, and we're looking for the amount of energy emitted by 2.3 moles of copper. So I'm going to kind of plug this in here. So E is equal to, so it's HC, I'm going to use HC lambda. So that's equal to Planck's constant, 6.626 times 10 to the minus 34 joules a second. Timesing that by the speed of light, which is 3 times 10 to the 8 meters per second. Dividing that by 4.5 times 10 to the minus 7 meters. Okay, so seconds cancel, meters cancel, and we're going to be left with joules. And it is 6.626 times the speed of light divided by 4.577. So I got, wait, that doesn't seem right. I made a mistake. Maybe not. Okay. Let's see if we do it okay. I feel like I'm doing something wrong, but I'm just going to go with it. Okay, so 4.4 2 times 10 to the minus 19, and that's joules per atom. Okay, I know what I did. We're fine. We're joules per atom. We're not done yet because we got moles, right? So how do we go from atoms to moles? Avocado's number, yes. Sure. So 6.02 times 10 to the 23rd atoms for every 1 mole, right? And we are actually, uh-oh. Nope. Oh, it's, I can't hit enter. Now I'm in the wrong screen. Oh, it's happening all at once. It's been awesome. Oh, no. Hey, it's back. No, it's gone. Oh. All right, we'll try one more time. Come on, you can do it. I'm hitting enter. Just recover the copy. Okay, that's fine, whatever, we'll take it. All right, here we go. Go. All right, so I had 4.417. No, we don't. Times 10 to the minus 19. That's joules per atom. Multiply that by 6.02 times 10 to the 23rd atoms, right, for 1 mole. And we had 2.3 moles, right? So times Avogadro's number times 2.3, we get 61623, and that's joules, so pretty much is that in kilojoules. There we go. Good? Okay, great. Good job. All right, that's done. That was a little ridiculous. Okay. Stop.